we've made some improvements, but there's also a problem with the shape of the tolerance volumes defined by either LCH or LA and B. Let's look at those and see how that affects things. Next slide shows two tolerances that could be specified for a set of actual visual data using LA and B tolerance volume. Triangle represents the target color. The diamonds represent acceptable production batches, actual batches that were made and evaluated visually by someone in this plant. And if there's no diamonds, that area is unacceptable. And what we'll see here is mathematically, if we use LA and B, we get a tolerance volume where the area that we're dealing with, because remember we're talking about space, the type of coordinates we're talking about here are called rectangular coordinates, so our tolerance volume is actually the shape of a cube. Think of lightness as coming out this way, so this would be three-dimensional. So we're looking at kind of a cutaway version. The question is, if our standard, this triangle right here in the middle, and all of these diamonds represent batches that are acceptable, we want to set an A and B tolerance for this product. So we got two choices. We can set one that's the smaller square, or we can set one that's the bigger square. You're the quality control manager. You just got a promotion. You're making big bucks now. Because you make big bucks, you got to make the hard decisions. Which one of these tolerance volumes would you pick for this product? The smaller one or the bigger one? Which one would you pick? Who would pick the smaller one? You got to answer one or the other. No, not answering. Okay? Smaller one. All of you? No one would pick the bigger one. Okay. Like I said, which tolerance volume would be best to match the set of data? Answer is really neither. It's a trick question. They always accuse me of trick questions. This was an actual trick question. The problem is, if you pick the smaller one, that would result in some batches that are acceptable falling outside of the tolerance range and rejected. If you pick the larger square, that would result in some batches that are unacceptable falling outside of the tolerance range and being accepted. So if we go back, okay, so if we pick our smaller one, like you said, if we made a batch and it fell right where this diamond is, what would we say? Our quality control decision maker would say it's what, good or bad? Good. And if we sent it to the customer, he would say it was good. So that's good. If it fell out here, what would our quality control number say? No good. What would the customer say if you sent it to him? No good. We're right there again. But what if we made this batch? What would our quality control number say? No good. But if you sent that to the customer, what would they say? Good. So that's a problem, right? So if you made that batch, what would you do if you were in the plant? You'd rework it till you got it in here. So you were what? Adding more cost to it than you really needed to do. Guys that work in industry, what do you think managers like about that idea? Not too happy, are they? They don't want to put any more cost into it than you have to. The smaller one isn't good in that case. The first two scenarios I said, it worked, but then the last one, if it falls here, it's acceptable to the customer, but not according to your quality control decision-making thing. Then if we pick the big one, after that happens, the boss comes and says, you're wasting money. Don't use that. Use something else. They say, okay, I'll use the big one. Let's say it falls out here now. What would your decision-making quality control deal say if you were using the big one? Good, right? And the customer would say, no, he would still say it's good because it's right up here, because it's still in here. All right, what if it fell over here? What would our decision maker say? Still good, right? Because it's within the big square. But if you sent that to the customer, what would he say? What the hell are you sending me? This stuff isn't even close. So that's no good either. But the problem is not so much with the size, but the shape. The way we actually see color forms more in this ellipse shape. We actually use actual visual data, acceptability data from customers. When we use A and B, the only shape we can make with those values, rectangular coordinates, is a square, or actually a cube. There's going to be times when it gives you the wrong decisions when you get into these corner areas because the shape is so far off. That's another problem with using L, A, and B and delta E that way. So like I mentioned, the reason is that the tolerance volume defined by L, A, and B uses rectangular coordinates, which results in a cube shape in three-dimensional space. And unfortunately, the shape that more correlates with visual observations is an ellipse. And it's kind of, if you think about it in three-dimensional space, it's more like a football shape, if you want to think of it that way. Or I always say it's more like a Australian rules football, rounded. That would be what the tolerance looks like when we're using rectangular coordinates. This is actual data from garment industry. And what we see now is that if we're using LA and B, we end up having to have different values for A and B, not so much L, but A and B, depending on which color we're working with. If we look at A, if we're in the red-orange, it's 0.35, but if we're blues, it's down to 0.20. And that's kind of opposite for B. As A goes down, B goes up. We started with trying to use delta E as a single number tolerance. Now, instead of one number, we got 16 numbers. What do you think the quality control department would have to say about that? No way in hell we're doing that. That's way too complicated. We're going to get everybody all confused and we'll screw everything up. Instead of having one tolerance, now we're up to 12. This makes quality control using these numbers very unwieldy. Just wroth with possibilities for error. You know, there's just too many numbers there to deal with. You're probably thinking to yourself, well, why don't we use L, H, and C? You know, that was better. Let's look at this to see how much better that L, C, and H is. We can split our total difference now into L, C, and H. Same total difference and the same L, so we're really substituting A and B, or C and H for A and B. Now the tolerance volume defined by LCH, that should be, is defined by polar coordinates, which results in a shape that looks like the next slide in 3 dimensions. That's what our new volume would look like. It's not a square anymore. It's kind of pie-shaped with the front end chopped off. But that's the shape that we get when we use what we call polar coordinates, which C and H are, polar coordinates. While better than a cube, it still does not result in an ellipsoid shape that correlates with visual observations. So it's better, but there's still problems with it. And look at some numbers that go along with LCH tolerances. And we can see, you know, again, delta E numbers vary greatly from 0.85 to 1.73. And then you can see the numbers for LC and H vary depending on what colors we're talking about. High here for yellow, C is 1.22. It goes down to 1.42 for tan. And you can see just in general that the H numbers are smaller than the rest of the numbers. Again, there we're talking about 12 numbers. That's getting unwieldy. We have the same problem with 12 numbers. It's better than maybe using delta L, A, and B, but it's still not the greatest. It's still not ideal. It again makes quality control difficult, complicated, and easily causing mistakes. LCH is better than LA and B, but it still has problems like equal weights to each value and the tolerance volume not elliptical. What this whole discussion really means is using, well, let's ask you, do you think it's good to use delta E for color tolerances? Yes or no? No but, yes or no? No, right. How about L, A, and B? Is that good to use L, A, and B? Do you think it gives a good correlation and works all the time? No. How about LCH? No, none of them actually do a very good job. And unfortunately, there's a lot of people in industry that, one, don't know that, and two, ignore it and use it anyway. You say you use delta E, that's not unusual. There's a lot of places that do that. If you visually have to look at it, what's the point of having the numbers? There are places that don't visually look at it. They just go by the numbers. And that can give you lots and lots and lots of problems. And from the color supplier's perspective, what ends up happening is they'll look at it visually and they'll make their determination visually, and then they'll kind of, how should I say this, manipulate the numbers so that the numbers agree. So if they look at their material and say, yeah, that matches, there's no doubt about it that that match, and then they get quality control numbers that don't match, you know, they may take another reading or something to get it to match. But also, if their numbers say, yeah, that's a good match, and then they look at it and say that's no good, you know, they're not going to ship that. They're going to still make it so it's acceptable, because they know that, you know, even though the customer says the numbers got to be right, even if the numbers are right, if they eventually ship it and it's still, like you do, it doesn't look right, it doesn't matter what the numbers say. So they have to kind of play both games, so to speak, get the numbers to match what they see visually, and sometimes it doesn't do that normally. If we looked at C-Lab space, what we would see is that, you know, if we did that experiment like McAdam did way back on the chromaticity diagram, or we drew standards and then where we could see a difference, acceptable matches, what we would see if we did it all through color space is that we would have tolerance volumes that look like this in terms of visual. We would see that they're not all the same size, sort of point to the center, but depending where you are in color space, they're different sizes. So they're different all the way around. It's not like in, say, one quadrant is the same, a mirror image of another quadrant. They're all different. So that makes it kind of difficult to use numbers to account for that. Just in general, as we change lightness, the tolerance volumes change. So as you get darker, the volume gets smaller. So that means as you get darker, a smaller number that you get from the equations actually means farther away visually. So if you were a dark color, the numbers have to be smaller for it to be acceptable visually. If it was a lighter number, the numbers could be farther off, but it would still look better visually. With chroma, same thing. With lower chroma, the numbers have to be closer to visually match. The higher the chroma, the numbers can get farther apart and still look good visually. So what do? It appears none of the numbers that we have discussed so far really do an acceptable job when it comes to color tolerances. So what do? Give up and go home? Well, you guys give up easy. Luckily for us, and especially for you, color scientists haven't stopped with these equations. They've analyzed the problems and developed more sophisticated equations, which I'm sure you're all very glad to hear. But are they any better?